right, this is Precalculus, chapter 14, lesson 2. We're going to talk about some properties of limits. All right, there are two special kind of functions that we can always know what the limit is. This is called the constant function. Graph, this is y equals 5. Always. That's what that looks like. That's called the constant function. This one is called the identity function. So, such that when x is 1, what's the value of y? The same, identical, identity function. When x is 0, what's y?
0.
When x is 1, y is?
1.
When x is 2, y is? Okay, you get the idea. This is the identity function.
Wow.
All right? Let's see how brown looks. Got it? So we're going to learn something. Okay, lock these in your brain. Because these should be easy questions to answer on a test.
Oh, like what's the identity?
So, if I ask for the limit as x approaches 6 of a constant function,
Is it just the same? It's 5?
it's always 5. It never changes. Doesn't matter what x is approaching. Y is always 5. Everywhere. I could have said where x approaches 100. It doesn't matter.
This specific one, but if it was
This specific one.
okay.
If it was f of x equals negative 10, then what would it be? What would the limit be? Negative 10 for every limit that I ask you.
Okay.
Got it? Okay. Such that the limit as x approaches any value of a constant is the constant. The limit as x approaches any value of a constant is the constant.
Well, wait.
The limit as x approaches any value of a constant is the constant.
Is this for constant function?
Constant functions only. Okay? All right, now let's look at this one. Let's say, what is the limit as x approaches 5 of this function? What does y approach as x approaches 5?
It's the same thing, isn't it? So, wait.
What is it? What is the limit of this function as x approaches negative 7?
Negative 7?
Because when I put negative 7 in for x, what's y? So, when we have the limit as x approaches c of x, of just x, it's always c. Yes. This is for the identity function. This is for f of x equals x. This is for f of x equals d. A number. A number. A number.
Is that not the same thing? Like you get the same thing?
No. Do you not see the difference between these?
I do, but like if you said if it's f of x equals 5 and then the limit.
That's this. That's this case. That's not this case.
No, I'm a little confused as well. I just like I don't understand.
Okay? Does y ever change for the constant function?
No.
It doesn't. So it doesn't matter what value x is approaching. It doesn't matter. As x is approaching 100, y is always going to approach 5 because y never changes in the constant function. It's a horizontal line. And this one, y changes. How does y change? Whatever x is. Whatever x is the same value of y in the identity function. So in this one, in this case, the limit is always going to be whatever x is approaching. Such that if we have an equation like example 1. If this is our function, f of x is x squared minus 2x plus 3. And we want to find the limit as x approaches negative 4 of that function. I could simply plug in negative 4 to this function. Or I could see this. I could break this equation up. And I could say it's the limit as x approaches negative 4 of x times the limit as x approaches negative 4 of x, so that this represents the x squared. It's the limit of each individual term. Are you following me? Minus the limit as x approaches negative 4 of 2 times the limit as x approaches negative 4 of x. That is the 2x. You see? I'm breaking the function up and looking at the limit of each individual part of it. Plus the limit as x approaches negative 4 of 3. Why can I do this? Because on the top of the table on page 9, the limit of functions added is the limit of each function individually added. The limit of functions subtracted is the same as the limit of each function subtracted. Multiplied, divided, radical. I can break this out. And now, what do I have? I only have identities and I have constants. I have constants. I have identities. So I can use the two rules. All right, so let's do it. All right, what's the limit of the identity? The constant. The limit of x is the constant. It's negative 4.
Oh, right.
What's the limit of the identity? Minus. This is the limit of the constant. What's the limit of the constant?
Just a constant.
The constant. What's the limit of the identity? The c. What's the limit of a constant? the constant. So I just applied those two rules in any formula. Got it?
Cool.
Okay? It's really no different than plugging the number in. I'm just saying. Because x squared is what?
Yes. Negative 4 times negative 4. Yes.
X squared is just negative 4 times negative 4. Minus 2 times negative 4. Plus 3.
So
What?
is it the same thing as just saying it's f of negative?
Yes. Literally, it's the same thing as substituting the number into the formula.
Is there a reason you would do this instead of just substituting the number?
Okay, it's an important rule to remember.
Just don't know it. Okay.
Because I'm probably not going to give you a formula. I'm probably going to give you f of x is 10. What's the limit as x approaches 5 of f of x? 10.
Okay.
Got it? I'm not going to give
solving it out. There's
no difference, right? You got it? It's as though we've said, okay, so does that limit make sense then?
yes.
The limit should make sense. Because the value is approaching as though we substituted x in the number. And whatever that value is. Hey, I'm not using that again. Okay. Let's keep moving. Once I get this erased, I am not using that marker again.
It's also not that you're replacing.
Oh, I'm just struggling with my board.
We're not doing that.
Okay. But it's a property of limits that we should acknowledge and know. I would 100% substitute it in. If what x is approaching is in the domain, I'm 100% substituting it in. I'm not going to go through this. All right. Let's look. There's only 4 examples, y'all. All right, what happens if we have a rational function? When we have a rational function like example 2, we have to ask ourselves, is what x is approaching in the domain? All right, so you see the function in example 2. I'm not going to rewrite it. What's the limit of that function as x approaches 2? So what I would quickly do is plug it into the denominator and make sure we don't get 0.
Oh.
All right? So what? That's 2 squared. That's 4 minus 12 plus 1. Okay, we don't get 0. So then I'm just going to substitute it in the numerator. 2 cubed is 8. 8 minus 3 times 3 times 2 squared plus 10. Do we get 6? I've done this math. Negative 6 sevenths. Do you see what I'm doing, Leah? Negative 6 sevenths, I believe, is the answer. Okay, so, ladies and gentlemen, what is the limit of that function as x approaches 2? Negative 6 sevenths. Why? Because it's in the domain. Got it? When it's in the domain, you just plug the number in.
Okay.
Got it? Now, what if it's not in the domain? Look at example 3. I'm sure it's the limit as x approaches 3 of that function. Okay. We have to decide if there's a hole in the graph or there's an asymptote.
Well, yes, it's undefined.
Okay, well let's see. We're gonna factor the numerator. What's the factors of the numerator?
1 or x plus 1 and x minus 3.
When do we have a hole in the graph?
Two things. Like, that's the numerator.
When every term can cancel out of the numerator and denominator.
So it says,
It's a hole in the graph. Hole in the graph. When all the terms cancel, there's a hole in the graph.
All the terms? What do you mean by that?
All the terms in the denominator cancel.
oh,
Okay? Are y'all listening? Y'all need to...
I thought you said,
When you can cancel terms in denominator, got it? Listen. I need you to remember these words. That's called a removable discontinuity. It's something that we can remove. It's not like we plug in the hole, but it's discontinuity. Yeah.
because it discontinues that.
It does discontinue, but we can remove it because we can cancel them. Okay, y'all watch when we cancel them. You need to know the words removable discontinuity, okay?
It is no longer undefined.
Okay, it still is undefined because it really is there. But the limit is easier to find because now all we have to do is plug in 3 to the terms that are left, and that tells us what y is approaching.
So you couldn't have just plugged in 3 to the first equation?
No, because it would have been undefined. So if I now substitute in 3 into the remaining terms, it gives me the limit. So 3 plus 1 is 4. What's the limit of that function? 4. Got it? Okay, let me just make up one. What if I had x plus 4 times x minus 1 times x plus 5 over x plus 5? That's my f of x. And I ask, what's the limit as x approaches -5 of that function? Do I have a removable discontinuity?
Yes.
I do. How do I find the limit?
You just
You
plug
plug
in
in
-5
negative
to the top.
Okay, -5 makes this term -1 times -1 times -6 is,
6.
that's the limit because we have a removable discontinuity. Got it? Okay. Before we do example 4, I want to go back to your homework from lesson 1. And I want to do number 1. It's just like this. Okay, they give you the numbers to plug in. Do you see that? They want you to plug in numbers all around.
Oh, yes.
You see that?
Oh gosh.
But could we figure that out without doing that?
Yes.
Well, let's see if we can. Let's see if we have a removable discontinuity. All right? All right, so this is the limit as x approaches 3 of x minus 3 over x squared minus 2x minus 3. All right. Let's factor. Always first think of factoring. Factor that denominator for me. We just did. X plus 1, x minus 3. All right. Where x is 3, do I have a removable discontinuity?
Yes.
Wait, but not all the terms in the.
But just at this one, I'm not looking at -1. I'm just asking it as x approaches 3, is that a removable discontinuity?
Yeah.
So we end up with 1 over x plus 1. So what is the limit of that function as x approaches 3? 1 over 4. Okay.
What are they asking for in the question?
So it's just the reciprocal
Of what we just did. Yes, yes, yes. They're wanting you substitute 2.9, 2.99, 2.999, all in for x and solve for y. But we know how to do this now. Okay, I want you to look at number 3.
Wait, what would we substitute in?
The numbers.
We remove the discontinuity and then substituted the value of x in.
But in the problem, like
You're going to calculate, but you should get 1 for it.
But how?
The-
How? If
Okay.
their numbers don't go.
Because as you're approaching 3 from the left and the right, you're approaching 0.25. It's going to be obvious. Got it? All right. Okay, but I'm showing you a different way than what these questions are asking. All right? So look, you need to know number 3 also. What's the limit as x approaches 0? Okay, this is always true when the problems look like this. Everybody look. Always true. And it's what you're always going to do. Is 0 in the domain? No. But you have to flip the switch because we're in calculus. And we don't rationalize numerators. We don't rationalize denominators. We rationalize numerators. So if I multiply this function by the value of 1, do I change it?
No.
So I remove the discontinuity by rationalizing the numerator. Okay? So I'm going to multiply by plus, right? What are these called?
Conjugate?
Conjugates. The conjugate of the numerator over itself. Do I have to FOIL when I multiply conjugates? No. I multiply first and I multiply last. So that's what I'm going to do. What's the square root of x plus 2 times the square root of x plus 2?
Where, x plus 2.
It's x plus 2. Minus times a plus is going to give me a minus 2 over, don't distribute the x. Do not distribute, do x times, don't distribute the denominator. Look what happens. What happens? The x cancels. I'm left with 1 in the numerator over square root of x plus 2 plus the square root of 2. That's my function.
How do you cancel x?
X and x.
But in that equation before that, how do you?
Well, no, I got rid of the 2. And it's x over x times that.
Oh, that's too much.
You leave a 1 in the numerator. This is simplification. Simplify terms that are multiplied. Okay, now, can I substitute 0 in? Yes, because it is no longer undefined and I can get the limit. That's the limit. Okay, got it? All right. Look at example 4. Back on page 922. Does anybody remember the difference quotient? This is not our first time seeing this. Vaguely, do you remember it? Vaguely. Do you remember what the difference quotient gives us?
What page?
Page 922. Do you remember what the difference quotient gives us? It gives us the slope of a secant line tangent to any curve at 2 points. All right, here's our function. Our function is f of x is x squared, and it wants us to find the limit as h approaches 0 of f of 5 plus h minus f of 5 all over h. All right, what's f of 5 plus h? This is 5 plus h squared. Minus, what's f of 5? 5 squared. All over h. What's 5 plus h squared? It's 25 plus 10h plus h squared. It's 5 plus h times 5 plus h. Minus 25 all over h. Our 25s cancel. Are you with me?
Yeah.
We're left with h squared plus 10h over h.
Take out factor out H.
An h can come out of every term. So we're left with h plus 10 So what's the limit as h approaches 0? Just put in 0 for h.